All right, we're going to start. I'm going to say welcome to everybody at the Charleston and Lewisburg locations. So we're kind of doing something a little bit different this week, and it should be, I think, kind of exciting. So we have Dr. Zhou, and she's an assistant professor in Davis College, the Division of Forestry and Natural Resources. She obtained her PhD from the University of Wisconsin and has papers in the areas of stochastic interest rates and Markov decision processes, and has done some geospatial modeling. It's exciting to have her with us as she's going to talk about Markov decision process models, theory and application in health economics. And I know that there has been people beginning to talk about health economics in different ways in order to model it. And so hopefully you will find her talk as exciting as I hope it will be.
Thank you. Thanks for coming. I'm so glad that I brought my colleague from our division with me, which has increased our audience by a quarter, right? By a quarter. So, yeah. And so today I'm going to be talking about Markov decision process models. So this is the model I use for my forest management projects. So forest management, health economics, totally different stuff, right? But not that different fundamentally if we can also categorize health state or categorize, or we can consider the number of days you spend in healthy states or so on as rewards. So this way, actually, they are quite comparable. And I'll explain the theory briefly, and then I'll talk about a few applications of using Markov decision process models in health economics. So first of all, what is a Markov decision process model? It's actually a decision-making tool. It's a tool that makes sequential decisions, and it's a tool specifically for stochastic systems. So first of all, why stochastic systems? Actually, if we think about it, everything about life is quite stochastic, right? Well, we can predict, okay, it's highly possible this thing will go this way or that way, but it's not deterministic until it has happened. So things are quite stochastic, and the outcome of things are very random. And they are random because they're affected by risk and uncertainty. So people have very different definitions for risk and uncertainty. Because I'm an economist, so for me, risk is usually defined as stochastic events, the probability of which can be estimated based on data or based on our existing knowledge. And uncertainty, on the other hand, usually refers to events which we could hardly predict because we do not have the knowledge. We do not have enough knowledge or data to predict the frequency or the probability. And the other thing, which makes stochastic which makes the systems or everything around us quite stochastic is because we actually do not know the world around us very well, right? We know part of it. We know some mechanism behind how things work, but we do not know all of it. So this is a very important, reason why systems are quite stochastic. And now, what is sequential decision making, and how to make sequential decision making? Well, sequential decision making is actually very, very easy, and it's very intuitive. First of all, we look at the system, which is stochastic. We observe the state the system is in, and we make a decision based on our observation. And then we observe how the system changes after we make the decision, and we make another decision when it's time. So we keep doing this until we have either reached a state death, or we have reached a state where we're satisfied with our decision or with our rewards. So, and how are decisions made? Decisions are made actually to achieve a specific objective. And the objective can be maximizing rewards. And in the context of health economics, it can be maximizing the number of days a patient spends in healthy state, or it can be minimizing cost. which in this context can be minimizing the cost of medical treatments. And another kind of objective can be to minimize risk. So the amount of risk that's involved in a treatment. And since we have a stochastic system and we make decisions, so the system or the state the system is in is jointly affected by both the stochastic nature of the system as well as our decisions. So this is, this is a very brief description of what Markov decision process is. And before I actually talk about how it is made up and how it works, I want to talk about the building brick or the foundation of Markov decision process. So it's a discrete time Markov chain. What is a Markov chain? A Markov chain is actually a way to describe a stochastic system. And this system, well, it's a random process and it's memoryless, meaning the probability of the system moving from one state to another state in one time step is only dependent on the current state the system is in. It does not depend on the previous states. So this is the so-called the Markov property. It's the most important property of the Markov chain, and the Markov chain is actually composed of two key components. The first one is state space, and the second one is transition probabilities. So what's a state space? A state space is a space composed of consisting states, and the state characterizes the stochastic system. And a state space is composed of finite numbers of states, and those states are mutually exclusively of each other, meaning the system can be only in one state at a time. So it cannot be well and sick at the same time, okay? Or you cannot be well and dead at the same time. You can only be either well or sick or either well or dead at one time. And examples here, well, a very simple three-stage system, well, sick, and dead. So this describes how a person, physically evolves, right? This is a stochastic system defined by three states, and a more complicated system can contain states like this. The states are defined by symptom scores. I am actually absolutely no expert on this. I just picked this up from the internet, and I suppose it gives you a score of how bad the symptoms are, so basically, if we assume that a smaller score indicates a very unlife-threatening symptom, and a big score represents a life-threatening symptom, then each score can represent one state, or a range of the scores can represent a state. If you have too many scores, say from 1 to 3, we can use this range as a state of relatively well, 4 to 6 representing a state of sicker, and so on. So this, it's actually very, very subjective how the states are defined, but just bear in mind that states have to be mutually exclusive. The system can only be in one state at a time. So this is the state space that characterizing the stochastic system. And then transition probabilities. So here, if I use ST to represent the state the system is in at time t, and then naturally ST plus 1 represents the state the system is in at time t plus 1. So your time step is from t to t plus 1, and this is the same as the probability of going from state I to state j. So the probability of moving from state I to state j from time t to t plus 1. So few observations are very important here. First of all, this is a discretized transition probability, meaning the transition will only happen from t to t plus 1. The transition will only happen for one predefined step. But this actually is not true in reality, right? You cannot expect the patient to go from well to sick just in 1 year, exact 1 year, or exactly 1 month, and so on, right? So what's happening in reality is oftentimes, or most times, continuous, but continuous, transitions are much more difficult to describe mathematically. So as long as the time step from t to t plus 1 is small enough, discretized transition probability will approximate continuous transition probability relatively well. So as I said, the first observation we can make is here the transition probability is discretized. And second observation we should make is for any given state I. So if you start from state I, then the total of transition probabilities from I to j should be 1. So that means if we go back to our example of 3 states, then the probability going from well to sick and well to dead should add up to 1, right? If you do not allow go from well to well. But if you allow that, that still should add up. The 3 probabilities should still add up to 1, right? Meaning you have to end up in one of the states. Okay, so this is another observation we should make. And then the third observation is very important. It means the stationarity. It basically says the transition probabilities do not change with time. So it is independent of time t. So this can be relaxed later on for health economics because, well, in health economics, it's often transition probabilities are often dependent on t. But for now, let's assume stationarity is true for the very general Markov decision process system. So, and the third observation we can make here is for a Markov chain, transitions are only dependent or determined by the stochastic nature of the system. Because here, do you see any intervention or management? No, we do not see any action or intervention or management. So this is how the system works without any human intervention. And this is a very basic introduction of the Markov chain, which is the building foundation of Markov decision process. And how do we use a Markov chain? So what good does Markov chain do? Well, Markov chain is very useful to predict the future path of a stochastic system. So if we start, so here I'm using the matrix notation. So P0, this represents the probability that the system is in, at the very beginning of your simulation. Okay, so P0, this is the initial probability. And times T, this vector T or the matrix T represent the transition probability matrix. Basically, this is the same transition probability we looked at on the previous slide, but I'm just writing everything in the matrix notation. So one single matrix will represent all the transitions among any 2 states. And if we let time elapse, so this is what the system will be in 1 step, will be in 2 steps, 3 steps, and so on. So this gives you the future path of the stochastic system. And this future path, again, is not deterministic. It's a distribution of probabilities. Basically, it will say, okay, the probability in 10 years that the person will be in well state is maybe 30%. In the sick state will be 30%, and then in the dead state will be 40%, right? So this, again, this is a probability distribution, but if eventually we let the system run long enough, we are reaching the so-called absorbing state, which is where the system will end up in the long term, and in this case, will be death. Okay, so that's the absorbing state. That's the only deterministic state the system will end up in if we give it enough time. So most other, for shorter times, the future prediction or the future path is always a probability distribution. And again, this simulation does not take into account managerial effects. So we do not get to intervene the system or manage the system or optimize the system. So Markov chain, again, is a very neat way to represent a stochastic system, but we cannot take into account managerial effects here. What if we do want to intervene the system? If we do want to optimize, well, then we can actually expand the Markov chain system to the so-called Markov decision process. And this is defined by a quadruple SPDR. S is what we already, we have already discussed. It's the state space containing states which characterize the stochastic system. This is the same. This stays the same. It's the same as the Markov chain. And then the second very important component is decision transition probability. If I cover this part, transition probability, the same as Markov chain, right? The law that guides the movement between states. But here, we introduce decision. So decision transition probability P, that's a very important part of the Markov decision process. And we also have decision set, and we have reward set. So again, the Markov decision process is defined by this quadruple here. And let's look at each piece in detail except for the state space because we already discussed that before. So decision transition probability P. If there's no intervention, again, we're looking at a pure Markov chain, the same as before, probability of moving from I to J in one time step. If there is intervention, if we do make decisions, then the decision transition probability is defined by this. And it represents the probability of moving from state I to J. This part is the same when decision A is made. So this defines the decision transition probability. Again, the time step is the same from T to T plus 1. So this decision transition probability allow us to intervene the system. And decision set, this is really important here, is actually a set containing, again, finite numbers of the decisions for states. And decisions have to be state specific to ensure feasibility. So if you are in, if you are in a particular state, only some feasible decisions are allowed, being either treatment or transplant or waiting or, and so on. So only feasible decisions are allowed for specific states. And another observation we have to make is, this is very similar to Markov chain, except now we have the decision here, and it states if you start from any state I, the probability of making any decision and end up in another state should add up to 1. So given a decision or given multiple decisions, you will end up in one state, okay? But the probability of ending up in one state is smaller than 1, probabilistic, and the sum should be 1. And here, this is the fundamental difference between a Markov chain and Markov decision. Transitions are determined by stochastic nature and decisions here, A. So this is a very important part. And now let's look at the reward set, R. A reward set contains RIA, which is the immediate return or immediate reward when decision A is made in state I. So you see the reward is only relevant to your current state and your current decision. And it is an immediate reward. And the reward can be positive if it is a benefit. And in the context of health economics, the positive reward can be expected quality of life years or other rewards. And the reward is negative if it is a cost. And for example, it can be some medical treatment expenses or costs. So you can have different rewards actually for the same I and for the same decision. You just have to categorize your rewards. So now we have examined the four components of Markov decision process. And let me review very briefly. State space, which characterizes the stochastic system, decision transition probabilities, decision sets, and reward sets, right? And now let's look at the planning horizon. So we let the system run. We manage the system. For how long? Well, it depends. But it can be finite, right? Your planning horizon can be finite. This means you only make finite sequential decisions. At the end of your planning horizon, you stop, right? So you make finite sequential decisions, and your rewards are sequential and finite as well. So say your time step is 1 year and your planning horizon is 30 years. So you only have 30 sequential decisions to make and 30 rewards to achieve. But if a large number of steps are involved, say more than, if our time step is 1 day and we manage for 30 years, a very large number of time steps are involved. In this case, this finite system can be approximated with infinite Markov decision process. What's an infinite Markov decision process? Very simple. It simply means the planning horizon is infinite. So you make infinite sequential decisions and you get infinite sequential rewards. And that's actually, to someone, it's a problem, because how can you make infinite sequential decisions and how can you get infinite sequential rewards? Then your total will be infinite, right? Is that right? Not really, because time has value. And in economics, we always talk about time value of money, which simply is $1 in the future is worth less than $1 now. And we can just put anything here, actually. Everything has time value. Your good health today will be, well, if we give it a specific quantity, your good health today will be worth more than the same quantity in the future. Why? Because of two very, very important and fundamental economics concepts. First one is time preference. We always prefer to realize our benefits as soon as possible and postpone our sufferings as late as possible. That's called the time preference. And the other thing is opportunity cost. It can be opportunity cost of money, because if you have money now, you can save the money, you can invest the money, you can buy good stuff for you, and that's the opportunity cost of money. So and if you have good health now, you can also make investment and so on, right? So the two concepts together make time, ensures that everything has a time value. So things happening in the future have less value than things happening now. That's why infinite sequential rewards actually do not add up infinitely. They add up to a finite number. And how? By using a discounting factor. So the present value of a future reward, RT, so this is a reward happening at time t, is the present value of this, how much it is worth now, is this value over 1 plus r, r being the discounting factor, raised to the power of t, t being the time in the future. So this means, well, the present value of a future reward is going to be worth less now. And the present value of all future rewards is going to be the sum of all discounted future rewards. This means even for infinite sequential rewards, the total present value of all future sequential rewards is finite, which mathematically makes our life a lot easier, because how can you maximize an infinite number, right? But we can maximize a finite number. So that's important. And now I want to briefly talk about policy. What's a policy in Markov decision process? It's very simple. It's just a mapping from state to decision. So if you just have 3 states here, and one policy could look like this. For state I, your decision is di. For state j, well, it should be j here, your decision is dj. And for k, your decision is dk. This is one policy. So you see, policies are just a combination of feasible decisions for each state. This is one policy. But a more interesting one is the optimal policy. So after all, we want to intervene to gain, right? We want to intervene to optimize. So the optimal policy, which is represented by D star, is the unique, meaning there's only one optimal policy. It's a unique mapping from state to decision that satisfies a specific objective. So for one specific objective, you only have one optimal policy. That's a unique mapping from state I to the optimal policy for state I, from state j to the optimal policy for state j, and from state k to the optimal policy for state k. So you see, it's a unique mapping, and it is deterministic, meaning for one state, there's only one optimal decision. That makes it deterministic and unique. So now we know what a policy is and what the optimal policy is. How do we find the optimal policy? Well, first of all, it depends on your objective, right? If your objective is to minimize the treatment cost, then you have a unique policy for that objective. But if your objective is to maximize the number of days a patient spends in healthy state, then that's your objective. You may end up with a totally different policy. But first of all, let's look at how to solve for the optimal policy. I'll make this really brief because it's quite technical. But we do have a lot of tools from either simulation or operations research. And the most powerful tool is linear programming. We can model the whole Markov decision process with a very neat linear programming model. And this is particularly powerful for infinite horizon. And it's actually ridiculously easy to solve. With just a very average desktop, it's super fast to solve, even with a lot of states and decisions and infinite horizon. So this makes this very powerful. And we can also use dynamic programming. This is also a very popular, very much used approach from operations research. You can either use a policy iteration algorithm or value iteration. So either way, it's another way to solve for optimal decision. And this should be consistent with the results from linear programming. Just a different way to solve it. And this is very interesting. And I think this is particularly relevant to health economics. Because after all, we do not know what's happening well enough, right? There are a lot of things that we are not sure about. For example, we can only observe, or we can only estimate partial rewards or partial transitions. We do not know how the rest of the world works. What if only partial rewards and transitions are observable? That means you have to learn from your decisions. You have learned as your understanding, evolves. And this is actually a particularly powerful tool. Reinforcement learning is actually a very useful tool in artificial intelligence because they train robots, right? They train robots who do not know anything at very first, and then the robots will learn from the environment and react correspondingly. So this is how it intuitively works. If we do not know our transition probability well enough, if we do not know our rewards well enough, no problem. We can learn, we can improve our policy by learning more and more and more. So I think this is particularly relevant to health economics. And there's another very useful approach which is called cohort simulation. So this is not exactly optimization. You do not exactly find the optimal solution. Instead, you find a near optimal solution or a solution that's well enough, that's close enough to the optimal. So in general, 4 different approaches to solve for the optimal policy. And so now I'll very briefly talk about a few applications I found extremely interesting in health economics using Markov decision process. So the very first category of application is to use Markov decision process to study cost effectiveness of medical treatments. So basically, people want to find what's the best or near best decision for each state, and this state are defined by the symptoms. So the total cost of treatment is minimized. So this is a very general category of applications of MDP. And here I give you this. This was published 20 years ago, and I was just looking at it at Google yesterday, and it had over 6,000 citations, and I was really stunned because in economics, if you get over 200 citations, you are great. But here, wow. So I was just blown away by this. But this actually laid a very good, well, as it says, it's a practical guide for using some of the Markov decision process, and especially the cohort simulation to study the cost effectiveness of medical treatment. So which I find to be very neat. And then another category of application is to optimize medical treatment decisions. So for a patient, when is the best time to start a treatment or to change his or her treatment? So the expected total time or total days in healthy state is maximized. So another category of the application, and basically this is what I found to be a really good review of the approach, as well as literary review of what has been done in terms of different diseases or medical treatments. So, and those guys are very close to us. They are at the University of Pittsburgh. So they have used a lot of Markov decision process to model when is the best time to treat or change the treatment of a patient. Another very interesting category of application is this. It looks a little weird. What does an actual decision made by a patient reveal about the patient's preference? What does it mean? Well, we know with Markov decision process, we can derive the optimal decision. But a patient may choose a decision that's not optimal. And how does this decision reveal about this patient's preference? Because patient's preference is supposedly to be important, right? In the medical decision making, and this is an inverse Markov decision process. after we have the optimal decision and we observe the actual decision made by the patient, we can go back and derive how the reward for each patient actually is, how the reward is for a specific patient, and that reveals the patient's preference. And this application is very rare. This is pretty much the only application I found in health economics, but I find it particularly interesting, and this is actually quite relevant to my own research, because if you go backwards and you can elicit the landowner's preference or the patient's preference, that's a very powerful tool, right? So although there's very few applications of this approach, I still find it quite interesting. Okay, so now I have talked about so many fancy things, good things about Markov decision process. What are the issues? We know every approach has its limitations or issues, right? And Markov decision process, well, many people have argued about its appropriateness or applicability in health economics. And I'm not going to repeat those. I'm just going to talk about issues from my own perspective, from my own experience. Markov decision process is highly data-driven. You have to have data to derive transition probabilities. You have to have the data to derive reward or estimate reward, and so on. So it is highly data-driven, which means your empirical results are highly dependent on what kind of data you used, right? And this can be problematic sometimes. And the second problem I find sometimes with Markov decision process is some assumptions are really difficult to relax in reality. For example, in health economics, they are making assumption that, in some application, that the patient has complete knowledge of the rewards, expected rewards for each decision, and they have complete knowledge of the transition probabilities. So the patients or the physician who is in charge of the patient knows the transition probability and rewards, which is actually not true in most cases, right? So these assumptions I find really hard to relax in reality. And Markov decision process models do need to make quite a few assumptions in order to work. So this is another potential issue. And the third issue is the propagation of uncertainty. This is an issue I have had with any kind of model, because our models are based on our knowledge, are based on the data, right? So if you do have a lot of uncertainty in the parameters, and you do have a lot of uncertainty in the model selection, and you have a lot of uncertainty in the scenario, eventually your model outcome will be heavily influenced by those uncertainty. So the propagation of uncertainty, this is going to be huge in any modeling-based approach. And in our discipline, in forest management, it can lead to biased results, but it's not life-threatening, right? The trees will live, they will be fine. But in health economics, maybe the propagation of uncertainty is going to be an issue, because it can be life-threatening if you made the wrong decision, you recommend the wrong decision. So anyway, there are more issues. As I said, no modeling approach or no approach is perfect, but those are the issues I have with this approach. So with that, I'm ready to take any questions you have. So thanks for coming, which has increased our audience again by a huge percentage.
Actually, do you have a question?
Yes.
So when you're talking about data-driven, how much data do you actually need?
Well,
Are we talking very large?
a lot of data. In one of, actually, do I have it here? Oh, here. In this publication, they have the liver transplant data from over 30,000 patients. So we're talking about huge data set if you want to accurately estimate transition probability as well as the expected rewards for each state and action. Yes, it is very data driven. But with some, there's some approach simulation, and especially with Bayesian simulation, they sometimes we can do well with limited data. Hundreds or thousands, yeah, still, it can be very demanding to have such a large database, data set,